Hello, my name is Todd Eden. I'm president, developer of HCT LLC, and one of our divisions is called Clean. Clean are products and services for the cleaning of water wells, whether they're agricultural, industrial, commercial, or municipal. Our goals are optimum, durable, and predictable outcomes. So we set out to solve this problem. The problem was called declining specific capacity. We were at an association, a waterworks association, and this slide was presented. And it basically showed that over time, that wells gradually die, in a sense. So usually wells will last about 14 years, and then they have production issues. They get in, they do a rehabilitation, and then they only get about 80% of the production back. And then sooner than 14 years, in about 8 years, the wells would get sick again. They'd do a rehabilitation and they'd get 80% of that 80% back. And then the following next term would be about 6 years. Again, 80% of that 80%, and so forth until the well has problems. So over on the right, we'll tell you a lot of things that are going on that cause this problem. And this was the problem that we sought to identify and resolve. So we've done a lot of wells over the years, and we've learned all of these things. So most new wells get sick at 14 years of age. Now it might be different in Alaska, it might be different in Fiji, but most of the wells that we've done throughout the United States, they get sick at about 14 years of age. And the go-to method for wells was brush and bail. So when the well got sick, they would brush and bail. And what we realized is that there's usually a lot of bacteria in the wells, and they colonize the perforations, especially where water isn't really moving a lot, whether it's above the cone of depression or down below the bowls. Bacteria find ways to survive in there and colonize those areas. And as they graduate towards the bowls, they've consumed and closed off these perforations. And so this is one of the reasons why brush and bail wouldn't work, because it really wasn't getting to the depth of biology in order to knock that biology down. So they'd get it clean, the well would look good. You now put a camera down, it says all looks good, but you really can't see in those perforations and behind those perforations where bacteria has still resides and exists. Crazy thing about bacteria is that it can reproduce its colonies over 15 minutes in the right temperature of water in the right environment. And so the amount of bacteria left behind kind of extrapolates on how fast that bacteria can recover. But there's other reasons that it happens, which I'll explain. So wells get sicker sooner than in the prior cleaning, as exhibited in the graph. And usually only 80% of the production is recovered in those rehabilitations. Over multiple decades, the well either is not performing, it's sanding, or it goes rancid, it goes septic, it has foul odor, which, that odor is actual toxicity. It's hydrogen sulfide gas, the same gas that would kill someone if they went in a manhole, because that gas consumes oxygen. So that's just the byproduct of the bacteria. And most sick wells are actually due to biological colonization, not scaling. Not in all cases, but in the vast majority, and we're talking in the 93 percentile, that most wells are sick due to being colonized by bacteria. Stagnant wells would naturally get sicker faster due to biological growth rate. So it's kind of like shutting your pool off. You shut your pool off, with it's chlorinated water, it's acidified, but you don't have circulation. And if you're not moving that chlorine around and suppressing that bacteria in an ideal pH, then that bacteria is going to grow. It's going to attach to the walls of the pool. And what do you have to do to clean that? Well, You have to shock it, you have to lower the pH, you have to brush it, you have to filter that bacteria out, throw it to waste. And if you can't do that with all of it, then it's just going to get upset again real quick. So the question is, how do we do that in wells? Well, we'll show you how. So odorous wells, usually made of steel, and also in PVC, but also stainless. Um, they get toxic, and it's usually because of bacteria and because of the sulfur and sulfate, but also the iron and manganese and phosphorus of water. So that's what causes our wells to become what's called anoxic. So it's an anaerobic bacteria called sulfate reducing bacteria. And you've probably smelled it. You've smelled it in drains and many different places. That's where stagnant water's in there. There's some bacteria, and that bacteria is feeding off of those nutrients, and it's growing and growing and releasing these gases. But that particular bacteria also produces sulfurous acid, and sulfurous acid eats iron aggressively. So when you see nodules on a pipe and you kind of pop the little nodule off and you see that clean stainless steel, that's the acid that the sulfate reducing bacteria was producing that's corroding that steel. And that corrosion rate can be as fast as 1/4 of an inch every 10 years. And one of the bigger problems with this is when you get into like wire wrap or louvered HSLA steel alloys, is that the attachment sites where this bacteria can get is usually at perforations. So where the metal was cut, not cut with a blade, but actually perforated. Excuse me. That's an open pore space, and the bacteria can find a way to get in there and start building its colonies. Compromised wells are usually evidenced by lack of production, sanding, and/or odor. And another thing to mention is, jetting became something fairly popular about 6 years ago. We'll call that in 2017. And a lot of people step back from that, including us, because when you're jetting bacteria and you jet that bacteria into the annulus, into the filter pack of the well, that's living bacteria, and it wants to grow and it wants to reproduce. So if we don't deal with breaking down that bacteria, then we're actually pushing it down into the well. And we go down with a camera after that rehab and we go, oh wow, it's the casing's really clean. But what we're not realizing is what's behind that casing, behind those perforations that now can proliferate. And we might see the duration of this declining specific capacity narrow a lot more, where that 8-year period turned into 4 and the 6 turned into 3 because of all that biology that's injected into the filter pack and annulus. Not saying that we wouldn't ever use jetting, because we have and we would, but we would never want to jet bacteria into the annulus without having the presence of a biocide to make sure that it's dead and it's not going to reproduce. So the solutions that we offer as a company are pretty vast. We start with a bunch of information of a well, and we do what we call interpretations and recommendations. So we're looking at all types of data, which I'll show you the details of, in order to come to scientific basis on what we would do and how we would do it. And then we need to take that information, put it in writing, and transfer that to someone who's going to put it out to bid, and then someone who's going to execute that work. So the details of that we call the scope of work. And sometimes we just need a short few paragraphs on what needs to be done and how. And then other times it has to be in great detail. Like, if you're doing work for a refinery or a microchip company or a very large municipality that's never worked with you before, they want all the details so that whatever contractor is going to do the job, if it's a new contractor, they're going to follow the instructions. If it's an existing contract that they've had a rapport with, they already know these processes and procedures and can execute them. So the interpretations, recommendations, and scope of work. A lot of times people say, well, we're going to do a well remediation, and when you go down and look, it's not a remediation, it's a restoration. The well's in dire straits. It needs a lot of work in order to get it back into condition. And we have to be careful in those situations because, older fragile wells can't take the physical energy, but newer, less fragile wells can. If we can use energy like steel wire brushes and really aggressive plungers, we can remove a lot of matter out of the well, and then we can use less chemistry. But then when you have fragile wells, you might have to use a lot of chemistry and less energy. But the goal is you've got to get this matter out of the well, because if you don't, it's going to get sicker sooner. So we have the well remediation and we have well restoration. We've also been involved in what we call post-failed remediation. So it's, where they went into a well, they did a rehab, they didn't get the results they were looking for. And so we got called and we're asked to come in and figure out what needs to be done. And then there's also situations where, they're trying to get rid of coliforms and E. coli and couldn't do that. And so we got called in and showed them how to do that. It's really interesting to understand what was done to the well because, for example, if it was jetted wrongly or if it was lightly brushed and not plunged, or they maybe used an acid instead of a biocide or a biocide instead of an acid, it's easy to understand what they did and what's left behind and what needs to be done in order to reach those optimum results. And then we have a technology. We actually have two, but I'm going to tell you about one of them later. We have seasonal protection. So like that pool that you shut off and it gets rancid and it gets sick, well, a lot of people shut off wells or they abandon wells for a period of time and they want to reestablish them. So those wells have very unique characteristics. And when you shut off a well, you shut off water with bacteria, with food source with bacteria during just a seasonal trend like a grower in agriculture. And they fire up that well and they get this push of red matter, and then it's followed by a push of black matter. That matter in those wells is actually colonizing that well, eating corrosion, eating steel, opening perforations, etc. So there's a way you can deter that. When the well's shut down, you can add chemistry down the well, draw it down into the well, and you can create water in that well, provided the gradient water flow isn't bad. It will deter that bacteria from colonizing in the well. And then when you fire it up, it's ready to go for the next season. So our processes are, discovery. We want to know every possible thing we can about that well. So we have a questionnaire. We take that data, we move it through different processes, which I'm going to show you. We run it through calculations. We apply the chemistry, the biology, the physics, the equipment, the time, etc. And that allows us to develop the scope of work, all the details of the scope of work, and also document a scope of work in writing for someone to follow to do the job. We always have to do this with foundational basis. The reason being, and we have to show that. The reason being is we're going to be scrutinized by the well owner, by perhaps a municipal biologist, their water department, their environmental department, their engineering department. Everybody wants to look at what we're doing here because nobody wants to get egg on their face. So they want to make sure that everything that's being done makes sense, that we've overcome any conceived processes and procedures, that we know we're bringing forth the absolute best available technology so that they can get those optimum results and optimum outcome and durable outcomes. And then we take and roll all that into either a short form scope of work or a detailed scope of work. So our track record is pretty good. We've done, I say, well over 1,000 projects across the United States of America. We've worked with literally hundreds of very experienced well people over multiple generations, and we've dealt with hundreds of engineers throughout the country. And what we've done over these years is we've taken all those best practices and we put them into a document. That document is on our website. Just go type in best practices, and that document is available for download, and you can read about all the things that we do and why we do them and how we do them, so that you can get a grasp of the whole process. So It is our ultimate goal to meet and exceed the customer's expectations, but it's important that we understand what those expectations are. So we know that we're going to have to provide them scientific basis. They're going to want references. They're going to want the extreme details of what we're doing, how we're doing it, chemical usage, what the chemicals are, et cetera, et cetera. They want data confirmation. They want to understand that, we're looking at everything the way it needs to be, the way it is, what resonates with them. They want to come to the conclusion that they're going to realize these predictable outcomes. All that has to line up with the details of the scope of work, and a lot of times they'll take that information, put it into their bid specification, and then put that out to bid. Not always, because once they get accustomed to working with someone and have these positive outcomes, they pretty much hang their hat on that entity, and that entity is usually chosen because they can be assured that the work's going to be done right and the outcomes are going to be as they expected. We've learned cost is not always the determining factor. We're usually more expensive. Not we alone, but the whole process is more expensive. But when you look at what it costs to put a bid out, to put a bid together, the engineering that's involved, all the logistics involved, all the time that's involved, you don't want to be in that well in another 6 years. You want to be in that well another 20 years. And so it's a huge savings to do it all really good the first time so that you can get those optimum durable results. Successful outcomes are essential. If you're the chief engineer, or you're part of the department that's rehabilitating this well, you have a lot of people looking at you, and you have to answer to a lot of people when things go south, especially the finance department and then your integrity. So it's very important that these outcomes come out positive, and we have to back that with scientifically irrefutable information. So a lot of people ask about the chemistry itself. Actually, our chemistry is environmentally beneficial. So there's a lot of cases where instead of moving the effluent from a rehab at any phase of the rehab into a Baker tank and hauling it off to a dump site and paying for that, we can put this out into agriculture. We can put it out into acreage. We can put it out into arroyos. It's beneficial. Everything in that well, the bacteria, the chemistry, the scale, all of that is actual nutrient value for soils. It's organic matter, it's dissolved solids, it's beneficial nutrients that helps things grow. And so we have, one of the products is the Klean concentrate, which is a supplemental inhibitor. We have the Klean pre-blend, which is the acid-based product with the inhibitor. It's not just an inhibitor. We have the WaterSol BC, which is a peroxide-based biocide. And then on the agricultural side, we have WaterSol Curative, which is very much like the Klean pre-blend. And then we have WaterSol AG, which is very much like the concentrate. The Klean products are all certified by NSF Standard 60. With that, they have an agreement with the American National Standards Institute, the Underwriters Laboratories, and also the Standards Council of Canada. These registrations come with great expense. They will inspect our manufacturing facility once a year. They'll do grab samples, make sure all the raw materials, the blended formulas are in compliance, that hoses are being stored right, that anything that's going to come in contact with potable water, it's mandated on exactly how those things need to be treated, how they need to be stored, how they need to be cleaned, etc. And so we subscribe to that, and that's what allows us to have that certification, and we have to pay for it annually, and we have to comply annually. We're also approved for the WaterSol products in the agricultural, agronomical business. So whether it's wells, whether it's agriculture, turf, landscape, sports fields, polo fields, soccer fields, nurseries, organic production of food crops. The WaterSol products are approved. They're approved by the California Department of Food and Agriculture. Some labels are approved for organic farming. And so when we talk about environmentally beneficial, uh, this particular slides lends a lot of credibility to that. You're actually eating foods where the water and soils are treated with our material. In food crops, pretty significant market share. We do literally several millions of acres of agriculture, from Florida citrus to wheat and soybean and corn in dryland farming in the Midwest and Kansas. We do tons of agriculture in California, Oregon, Washington, Idaho. Um, so all across the country, we do over 240 golf courses throughout the United States, sports turfs, polo fields, etc. And and throughout the United States, I mean border to border, coast to coast, from Maine to San Diego and Washington to Florida. So a lot of times when we first meet clients and they have a well, we need data. And they kind of question themselves, well, why do you need this data? Well, the more information we have, the more scientific basis that we have for making the decisions we make. So when it's all said and done, we can look back and say, we took every single one of these components and we put them together to write this prescription and this process and procedure to get this outcome. And so the outcome should be positive. If it didn't, what are we missing? We have to be missing something. And so we have this little document. You can download it online. And if someone's wondering, well, why are you asking all this information? Well, here you go. Here's why we're asking. There's a diagram, and then there's an explanation for why we're asking for all that information. And this is the first page of our elaborate spreadsheet. So this is what we call the discovery document. When did the opportunity come in, who it came into, who the well owner is, who the dealer is, who the engineering contact is. Tell us about this well. What supporting data do we have on it? Do we have the driller's log? Do we have a video? Is the video of this decade? Is it a picture? Is it actual video? Is there a contingency plan if something happens to this well? What are the wells? What are the details of the well schematic? What is the treatment history of this well? What is the water quality of the well? What is the date of the water quality well, et cetera, et cetera. All of this data then flows into other worksheets that pre-populates so that we can interpret more information. And this is one of those sheets. This is called the Langler Saturation Index. It's an index used in water treatment. There's two other indexes. There's one called the Risner, and there's one called the Picorius. And what it is, it's a scale or corrosion deposition index. So it takes certain parameters of water temperature, pH, alkalinity, and it tells you whether that water is capable of scaling or not, and how severe it could corrode or how much it would tend to precipitate scale. So this is one of the tools that we use to define whether a well needs to be descaled or bioremediated just based on water quality. Now, the index doesn't take into consideration the biology. It just takes into consideration the water parameters. So we add additional categories that are noted in blue: the sulfate, the silica, the sodium percentage, the sodium, the bacteria, the manganese, and the iron, all food sources for bacteria. So if I have a stagnant well and we have a lot of sulfate, we have a lot of manganese, odds are we're going to have biological issues. Let me throw iron in there too. And so this gives us a good indication of what that well is going to look like. Then you add age to that, period of stagnation, and whether it's been lined, and the alloy of the casing. All these things play into the prescription, kind of like a blood work analysis at the doctor. And this is a little algorithm that we built. It was kind of fun when we first built it. We found it flawed and we found the defect and corrected it. So it works pretty good. But look at the different dynamics we're looking at: age of the well, the casing material, the perforation types, whether it's been lined, if it's been jetted, what the water quality is telling us, and then what the groundwater biology has. And so from each one of those, I think there's 27 of them, Then we give it a rating against biology and scale. Okay. And so in this scenario, the age of the well was over 24 years old. So we gave it a biofactor of 4 and a scaling factor of 1. The casing material was steel, so we gave it the worst rating, and then for bio, and then a good rating for scale potential. When we get to perforations, notice wire wrap and then steel. Wire wrap gets a 4. If it was stainless, it wouldn't. And then on the scale side, it got a 3. And there's reasons for that. If it's jetted, again, you'll get a biological 4. From the scaling, you can break down all the calcium scale you want and throw it into the annulus, and it's not going to cause any issues. So anyways, that is our assessment dynamics. Say, all right, we're going to give it a factor of 18 on the bioremediation. Well, then the amount of chemistry will change and the cost will change. But it's all the stroke of a keyboard. Put in a number, calculations are made. All of this rolls over into another sheet that we have where we can put in the actual schematics of the well. So, we've got from 0 to standing water level, and then standing water level to blank casings, then the first perforation to this range, and then maybe blank casing for this range, and then back to perforation to that range. It calculates all the water volume based on the louvers of the casing. It calculates the amount of filter pack space, and then calculates the total water use. And then we could choose each one of those, if not all of them, for the remediation product. So we'll TREMI a lot more chemistry into a screen zone than we would TREMI onto a blank zone. And so all those totals roll up, we put in the processes, the amount of chemistry, and then that calculates all of the material that we're going to need. And then that all rolls over into all the data we need for the scope of work. How much chemistry, volume-wise, total, how much chemistry per segment, how much chemistry per, let's say, tool length or spotting length. So maybe the client's going to use a 5-foot tool or a 10 or a 20-foot tool. Again, all we have to do is change the cell and all the numbers capitulate. They all calculate, and then we could take those numbers and move them over into the scope of form or scope of work. Now, sometimes once we predict what's going on, they do a downhole video, then we'll repropose. We'll say, well, based on what we saw, we think we should manipulate this and manipulate that. The nice thing about it is all the numbers flow. Or the job's been let, the client calls and says, hey, we're not going to use a 10-foot tool, we're actually using a 15-foot tool. Or we're going to use 2 5-foot tools adjoined. And so really it's just a matter of plugging in the numbers. And that rolls into a real quick and easy cost proposal. So end user pricing and contractor pricing, it's a matter of minutes to produce and to send. Detailed scope of work can get pretty elaborate. Here's one for Marathon Refinery. I think they've done 4 or 5 wells with us. You can see it's 14 pages. So, and this was, crossing every T and dotting every I. Every single iota of what was going to go on was in this scope of work. We've had a short form scope of works that's just a single page. It's just an outline of what we're doing, and then we send them the documents, and they've got all the different calculations that they need. This is just a list of our services and chemistries. So as we mentioned before, we have the interpretations, recommendations, and scope of work. We have the well clean pre-blend, the water salt BC, the well clean concentrate, and then the lab chemistry. All these are available on our website. In addition to our website, we have, if you go to our well page, you'll see these little tiles, and behind each tile is a bunch of information. So down on the bottom right, you see best practices. If you click on that icon, it's going to take you to a page with all the documents about best practices. Likewise, in the upper right, you have case studies. Same thing. Click on that and you'll get a list of case studies. So here's a list of documents under best practices. So environmental products, best practices, well rehab, minimum data and why, biocides for industrial use. That's a document that was done by the US Corps of Engineers on disinfectants and biocides. So all these things are available to you. Another tool that we have on our website on every page is a search bar. And we put a lot of time and resources into this. So when you're looking for something, you don't have to go searching for it. Just type in best practices and you're going to get to that document and any other related documents. Type in well rehab, you'll probably get a list of 50 documents. Type in well tools, you'll probably get a list of the pictures of all the different well tools that have been developed by some of our customers. Speaking of well cleaning tools, here's some images. So you'll see brushes with plungers, and you'll see we designed this plunger layout for specific reasons, which you can read about in the best practices document. When you notch those plungers, first of all, you want to plunge a well. You don't necessarily want to swab it. Swabbing a deck is like mopping the floor. We want to plunge the toilet. We want to move chemistry, move volume, move energy, so we can get chemistry through perforations, get matter into water. Some brushes, there's a tool towards the bottom on the left that it's not nylon brushes, it's actually cable tool that's put through holes in the piping and then frayed. The well was capable of using a very, very aggressive brush, and we want to remove as much physical matter as we could before we started applying the chemistry. So one of the other processes that we recently developed, and I think it's been about a year and a half to 2 years, we haven't had a lot of movement on it, but it is available, is in situ well rehab. So if we know that we have wells that are biologically compromised and we know they're going to be offline for periods of time, or we know that our specific capacity comes down a bit, we can go in now today and we can actually acidify and or bioremediate and or both with voles in the well. And the biggest problem in the past with that was that the most active alloy in bowls and in a well pump is usually the shaft, and that's because the shaft is a softer stainless, 416 stainless, and in the presence of acid, it degrades very quickly. And so we found a way to be able to make the acid not attack that 416 stainless. And so that allowed us to develop a bowl pump in place remediation program or preventative maintenance program. So what a nice savings and extension of well longevity and production and efficiencies by being able to clean that well periodically with everything in place. So there's lots of terminology, and I don't want to bore you with all the details, but we talked a little bit about the LSI, which is the Langler Saturation Index. We talked about plunges and swabbing, touched on pre-cleaning, touched on jetting. We touched on aerobic and anaerobic bacteria, but all of these terms are really, really important to know from a technical standpoint, like biocides versus disinfectants, surfactants and dispersants, chemical retention times. All of these are covered in our data, in our information, and we'd love to help you get your arms around this as well as share the information with you. Here's more termination, more things to consider. So we have stagnation, layup chemistry, gradient water flow, bacteria, corrosion, tubercles, colonization, aerobic and anaerobic, acid-proof biofilms. That's something we haven't touched on. Biofilms of iron-reducing bacteria are impervious to acid. And until you get through that biofilm, which requires a biocide or scarifying, you can't even get the acid to the scale if the scale exists. So, these are all really important things we know. Downhole neutralization, they said we were crazy. But when you acidify steel, you've got to repassivate it. If you don't, steel and water rusts, and rust is food source for iron bacteria. So immediately we start feeding bacteria to the well for it to colonize the well again. But if we passivate that surface, then that process doesn't occur. And so this is part of the acid neutralization, but we do it downhole and we do it a specific way. The rate of scale dissolution. We tested a couple competitive products for how much scale it removes, how fast it removes it, and then what's the corrosion during the process. And we found cases where we're removing twice the amount of scale in half the amount of time for the same price. So you might be paying $20 a gallon for a product that only removes half the amount of scale in double the time. So time is money. Chemical performance is essential, and so it's important to understand that dynamic. Another thing that we do is we have safety and certification. So we want people to understand the chemistry, understand the safety, the PPE, why they're doing what they're doing, what those expected outcomes are, what they can expect to see and experience. And so we have a certification program. We certify applicators, and it's something that you're more than welcome to subscribe to. There's no current fee for it at this time. It's done online, and you do receive the certification, and you get registered with us. Excessive use of chlorine can be an issue. A lot of people say, oh, I've got bacteria issues in my well, I'm going to pour some chlorine in it. Clears up the problem a little, but the actuality is that chlorine is very corrosive to steel. And I'm going to show you a video on that. But the other problem is that too much chlorine will actually burn the biofilm and kind of like cauterize it. So now what you've done is encapsulated those colonies and actually help protect them, because you gave up the surface bacteria to protect the underlying bacteria. And they will find a way to grow below that barrier and around that barrier. And so you really didn't help solve the problem. The solution is to get as much of that bacteria out of the well as possible. Over-chlorinating is not the way to do it. You're better off using a low level of chlorine all the time, like you would in your pool, than to shock it. In fact, if you did your pool and you shocked it and you didn't re-add chlorine, you would see that once that shock ran out, the bacteria would just explode. Okay, this is a time-lapse video that we did with water and mild steel, chlorine and mild steel, and the water salt BC and mild steel. And you can see that the chlorine started eating up this steel extremely quick. And where it did it was where that hole was punched. So not so much at the surface of the steel, but where that metal was cut and where it was punched, because those surfaces open the intergranular structure of that steel, and that's where the bacteria and the corrosion got in and started the processes, which would represent the perforations of your casing. Okay, this shows the synergy between acid, biocide, and the combination of both. Now, as I mentioned before, if I have biofilms on scale, the acid will never get to it. The acid will never get to the scale. So I've got to get through those biofilms first, then I'll be able to get my acid to the scale. So this particular photo shows you a deposit that we received. It was in a jug, had a bunch of deposit in the bottom and a bunch of black water on top. And so we separated that into 3 beakers, and we acidified one of those beakers with water and tons of acid, not literally tons, but a lot. And you could see over, I think it was probably a week we let these soak, and you could see that the acid left behind matter. We did the same thing with the water salt BC, and you can see that the biocide left behind matter. We did the same using the acid and the BC, and you can see everything got solubilized. Everything went into solution. And the nice thing about this with this chemistry is if I evaporate that solution to dryness, it'll be a powder. And if I add water, it'll all go back into solution. And so we don't get these reversion products. So that's one of the deals in wells with downhole neutralization. They thought everything would fall out and then recrystallize in the bottom of the well. That's not the case. This is some of the things that we do in agriculture. So we have soils that are cemented, we acidify, we biocide, and then we convert those into soluble salts. At times they dry out, but when you add water, they rehydrate and the plant drinks them. The plant literally blows out of the ground. Makes a lot more production with a lot less water. On the bottom left, we're showing you a medical view of biofilm. So that's what the acid can't get through and what the biocide has to get through and break down. So the red arrow on the right, that's processes and procedures for predictable outcomes. So if I know I've got biomatter and biofilms, I'm going to go in and I'm going to bioremediate first, because the scale underneath is I'm never going to reach it with my acid until I break down those biofilms. Okay, all of these videos are available on our YouTube channel from our website. Go to our website, click on the YouTube channel, look for these pictures. They're pretty priceless. So the first upper left is my hand in 0 pH, highly acidic water, which is dissolving seashells. So I actually lift the shells out and show you the shells dissolving. We'll put the shells into total solution. I can leave that chemical on my hand all day long and it won't hurt me. The middle video is a time lapse of that corrosion of the chlorine against the water salt BC. And then the other two videos show you the effect of our acid against steel, iron, so iron fertilizer, and calcium. And it was pretty shocking. That's why we posted these videos. The sulfuric acid would not dissolve calcium in the presence of iron, but it would eat steel. Where in our case, we would not eat steel, we would dissolve iron, and we would dissolve calcium. This is really big in the agricultural industry because plants need to drink calcium. They need to drink iron too, but they need that calcium. So these and many more videos and testimonials from golf courses and agricultural farms, etc., are all on our YouTube and our Vimeo websites. This was a study we did many years ago. We took 10% hydrochloric acid, and then we took our additive with the hydrochloric acid at 9%, and we started dissolving calcite. So a calcite cube, about a 1-inch cube, we knew we had more calcium than we had acid, so we knew we would consume all of the acid's ability to dissolve the calcite. And we'd have calcite left over. So we wanted to see the difference between what the HCl would do versus the HCl with our material. And you can see at the end of the dissolution that the pH of the HCl was 2.7 and the pH of our material was 1.5. Now, you would think at that low pH, like we used to see in specs all the time, maintain pH at 5. Well, if you reach saturation, you can have a pH of 0 and it won't dissolve scale. So, you know, we debated that a lot of times and we finally found a way to show it. But you can see here that overall what happened is we were able to dissolve with less acid in our catalyst inhibitor 13% more calcium hardness than the acid by itself. And you could see that it kind of capped out at 23,000 parts per million total hardness and 34,600 TDS. So there's a couple things about this. If I had a well that was scaled, I would rather do 2 5% scale processes than 1 10% scale process, because I'm afraid that I will reach saturation and I'll have the free acid, but it's saturated. Now, let me explain saturation to you again. Take iced tea, put 1 spoonful of sugar, stir it, it all goes into solution. Put the second spoonful of sugar in, it doesn't. It sits on the bottom. Okay, that's what's happening. Take sodium and put it into water. You can put spoonful after spoonful after spoonful, it all goes into solution. Okay, but take calcium and put it into water, and it's going to sit on the bottom. Okay, so, and yet sugar, like I said, you put 1 in, it goes into solution. You put a second, it doesn't anymore. It's saturation. And so that happens in wells. You consume the biocide, you saturate the acid, and then it's not working, irrespective of pH. Okay, so when they're telling you to maintain that pH at a certain level, here's a good slide you can share with them. All right, so learning all this, knowing all this, conveying all this, we don't feel that's your job. We feel that, you want to bring someone to the technology, and we'll do the technical side of it. We're happy to do the technical side. That's why we're here. We work for you, for your client. And so when you have these opportunities and can engage with us, we'll do that heavy lifting. We're not out in a truck. We're not knocking on the doors. We don't have the relationships you do, but we have the intellectual knowledge. We have the chemistry. We have the systems, and we've developed these systems. So, it used to be 2 days to do a well assessment and proposal, and today it's maybe an hour and a half, 2-hour deal at the most. Unless you want a detailed scope of work, then it's a lot more work, but it's a lot less than it used to be. So we're here for you. All right, we do generate for our clients more revenue, and it's caused by more site time. It's caused by repeat business. You might say, well, if you make these wells last longer, we're not going to have more wells to do. But what we've noticed, kind of like in our golf industry, the better the course, the more play they have, because people like that quality of play. Well, the same thing in wells. When they're getting great results from you, they want you back. They want to start working on other wells and other wells. And when they know these outcomes, they're not running them to failure. You can add preventative maintenance programs. You can lay periodic layup chemistry into their wells and alleviate these problems and extend the life of this capital asset, which is a huge, huge word. That they're going to have this well. It's going to continue to perform. They're not going to be paying exorbitant pumping costs and pumping sand and having all these this deterioration going on. So it's it's a pretty big deal, and I think they see it when we provide them all the information on a proposal. So we have products, we have different applications, and we have different services. So we're involved in the ag business, we're involved in the turf business, we're involved in the well business. We do analytical testing, we do consulting. We deal with water, biology, soil, corrosion. We do interpretations, recommendations, and prescriptions. We have our 2 basic WellClean products, which is the WellClean Pre-Blend Acid and the WellClean Concentrate, which is an inhibitor and a sequestrant. Also in that lineup is on the left, which is the WaterSolve BC. And on our agricultural side, we have our WaterSolve Curative Acid, our WaterSolve BC, but then we have some end-use products, which the fix is the curative with a little BC, and the grow is the BC with a little curative. And so if we have a golf course green that's primarily calcareous, they can spray with the fix, but if we have one that's mainly biological, they can topically spray with the grow. If they have problem areas that are calcareous, same thing, they could use the fix. If they've already turned septic and their biological issues, they could use the grow. We have trade named our test methods. They're enhanced and improved methods called the legacy test methods. It's for water, for soil, and for available plant nutrition. For wells, we add the bacteria to the water, so it gives us a good indication from that aspect. And then we develop chemigation systems in order to apply all this technology. So that's it. We are HCT. We're based out of Scottsdale, Arizona. We're here to help you help your clients. We'll do the technical documenting lifting on our site for you. We'll hand it over to you and or your clients. We are part of your team. We're here to help you, and we appreciate all the relationships and opportunities that you would consider presenting to us. Thank you, and we hope you have a blessed day.